For decades, our instruments have picked up startling data from the bottom of the ocean. Microphones have recorded massive sounds echoing across thousands of miles. Sonar has pinged enormous disc-shaped objects resting in the silt. Divers have photographed what look like terraced stone pyramids. We still have not mapped or explored roughly 95% of the deep ocean. That leaves a staggering planetary-scale vacuum of hard data. When we look into an empty void, we instinctively fill it with familiar narratives. We see geometric rocks and assume they belong to a lost civilization. We hear loud noises and imagine giant undiscovered sea monsters. We project our own terrestrial myths down into the dark. To accurately map the extremes of Earth, we have to leave those surface instincts behind. The actual, verified geology and chemistry of the deep sea is more complex than any myth we could invent. At the end of the Cold War, the U.S. Navy handed over access to SOSUS, a massive network of underwater microphones originally designed to track Soviet submarines. Civilian researchers began using this network to listen to the ocean. In 1997, they captured this reading. This is a waveform diagram of an acoustic event that researchers nicknamed the bloop. Notice how this low-frequency sound spike dwarfs the normal ambient noise of the ocean. It was powerful enough that hydrophones picked it up across a range of 3,000 miles. Because the audio profile shared characteristics with marine animal calls, researchers initially theorized it was biological. But looking at the scale against the call of a blue whale, any creature capable of producing the bloop would have to be physically impossible. The true source of the sound was cryogenic. When massive glacial shelves fracture and violently shear apart from the Antarctic coast, the cracking ice generates an acoustic shockwave that travels cleanly through the deep water. Other famous mysterious ocean sounds, like Julia and Slow Down, were exactly the same: massive icebergs violently scraping against the ocean floor. The bloop mystery demonstrates how easily we can project biological intent onto noise, turning a collapsing glacier into a monster simply because we expect it to find one. That same sensory bias applies to what we see. We expect nature to be chaotic, so when we find right angles underwater, we tend to assume they were built. Take the Yonaguni Monument off the coast of Japan. The geometric edges and flat terraced steps look exactly like a stone pyramid. Or consider this sonar scan taken at the bottom of the Baltic Sea. The data shows a massive, disc-like shape resting on the seabed, complete with what look like structural lines and drag marks behind it. The geological reality is that extreme environments fracture rock in highly organized ways. Tectonic pressure pushes sandstone up in perfectly straight shear planes. Glacial erratics, massive boulders dragged by ice ages, carve perfect grooves into the seafloor as they melt and settle. We see a right angle or a perfect circle and instinctively associate it with intelligence. That reflex blinds us to the architectural power of raw tectonic pressure. Sometimes, the ocean floor mimics the surface world, creating environments that look like familiar landscapes but function as deadly traps. While mapping the Gulf of Mexico, researchers aboard the exploration vessel Nautilus discovered an anomaly they eventually named the Jacuzzi of Despair. Looking through the submersible Alvin, the anomaly looks like a traditional lake. It has a visible surface, a distinct waterline, and a sandy shoreline. This diagram shows how an underwater lake physically forms. The water inside this depression has incredibly high salinity levels. Because that concentrated salt brine is denser and heavier than the surrounding ocean water, it sinks and pools, establishing a stable boundary layer. That pool contains zero oxygen and is filled with toxic methane and hydrogen sulfide. Any deep-sea crab or fish that wanders over that shoreline suffers immediate osmotic shock. The salt and toxins kill them instantly, leaving their bodies pickled along the edge. In nearby regions, geological faults release pressurized, semi-liquefied petroleum. When this tar hits the freezing seawater, the outer crust hardens while the inside keeps glowing. It creates rope-like structures that look exactly like basaltic lava flows. The deep ocean wears the visual mask of our surface world, lakes, shorelines, and lava fields, to hide a hostile chemistry. To understand the abyss, we rely on exploration ships like the Atlantis to carry submersibles into these depths. They are finding environments that function unlike any other ecosystem on the planet. Deep in the Atlantic, researchers mapped the Lost City hydrothermal field. Most deep-sea vents are powered by volcanic magma. The Lost City is different. It consists of towering, ghostly white carbonate chimneys, venting highly alkaline fluids into the dark. This diagram illustrates the low-temperature chemical reaction driving this field, known as serpentinization. As seawater filters down into the crust, it hits iron-rich mantle rock. The rock reacts with the water, changing its mineral structure and releasing diatomic hydrogen and methane gas. An entire ecosystem of microbes, snails, and tubeworms thrives here, feeding directly off those chemical gases. They exist in isolation from the sun above or the magma below. The chemistry at the Lost City is so efficient at generating organic compounds out of raw rock and saltwater, many researchers now believe these exact structures could be the environment that sparked the origin of life on Earth. As we map our greatest frontier, we are finding that the abyss is not a graveyard for lost cities or mythical monsters. It is a laboratory where the chemistry of the Earth itself explains how we began.